Okay, so we've had several videos now about work, power, efficiency, energy resources, and so on. So it's time for a little bit of practice with these concepts. So here goes. We've got quite a few problems in this video, so it'll be a little bit on the long side, but we'll go quick through these. Okay? Alright, so here's question number 1. Which form of energy is used to generate electrical energy in a tidal power station? Okay, this is one that we went over briefly in the energy resources video. So it's using wave energy to splash up over a barrier and then sort of fall down through a turbine. So you can kind of use process of elimination here if you don't remember all of that. Is it nuclear? Obviously not nuclear, right? Only a nuclear power plant uses nuclear energy. Chemical energy, nope, that would be coal or oil. And it's not basically internal energy, is like when something warms up inside. It's not worth much, like basically raising the temperature of an object, usually by friction or air resistance or something like that. So it's not that. It's gravitational energy. Basically waves splash up over a barrier, sort of splash up here, and then they go down into a reservoir. If you remember this, they go down into a reservoir here, and then there's a turbine outlet and a turbine inside here that spins. That's basically how it works, and then it goes back out to the ocean. So that's the idea of a tidal power station, if you don't remember that. Alright, moving on. Which source of energy uses the production of steam to generate electricity? So here's the question. Which of these uses heat to make steam that then powers a turbine? So does a hydroelectric dam, basically a dam in a river, does that use steam? No, it does not. Hydroelectric uses gravitational energy falling down through a pipe, basically. Water is way up high, right, behind the dam, and then it goes down through a pipe with a turbine in it, in there. It's a turbine. And then, well, this is a really bad drawing of a dam, but anyway, the water is there on that side, way up here, and then it's down low on this side. So the water just comes through that pipe, falls through basically because of gravitational energy. Okay? Cool. Alright, so it's not hydroelectric. We'll just go in order here, and it is actually nuclear. Nuclear power uses the heat of the nuclear fission reaction to boil water, basically, and then that steam is ultimately used to spin a turbine. Cool. Now we've got the opposite question. Which of these power stations does not use steam from boiling water to generate electricity? This is, by the way, the most common way for a power plant to produce electricity. You make steam, you boil water, and it spins a turbine. Right? So geothermal uses heat from rocks to produce steam and power a turbine. So that one does use it. Alright, nuclear we just talked about in the last question, that does use it. An oil-fired power plant uses the chemical energy of oil to burn that energy and then heat water till it produces steam. So those all three do produce steam. So the one that does not use steam is hydroelectric. Alright. Cool. Now we've got a picture of a hydroelectric dam. Alright. What we have here is a dam, side view of it. There's a pipe going through it. Alright, and then behind the dam there's a reservoir of water. Alright. This is much higher than the water on the other side of the dam. So then you've got this pipe that goes through here, the water falls, quote unquote, falls down through here, and then it flows through this pipe, spins the turbine as it goes by, and that powers the generator. So the question is, what is the sequence of energy conversion. All right, how is energy converted in this process? Well, you have to look back at the problem. What are we starting with? What's our initial form of energy? And that's basically the energy the water has because it's high up, right? The water is high up on this side of the dam. So what kind of energy is that called? That is gravitational energy. So we know we're starting with gravitational energy, which means we can't be starting with B and we can't be D. So we're either A or C. So then the question is, does the gravitational energy become electrical energy next, or does it become kinetic energy next? And remember, kinetic energy is energy of motion. So yes, the gravitational energy becomes kinetic energy, and then that is converted by the turbine over here into electrical energy. All right, so the answer is letter A. Cool. All right, enough with energy. Let's move on to work and power. Okay, so we have a laborer on a building site who's lifting heavy concrete blocks onto a lorry. If you're British or from the Commonwealth, you might know what a lorry is. Otherwise, it's probably a new word. It means truck. That's a truck. Okay, so he's lifting blocks onto a lorry. So he starts with a heavy one, and then after the heavy one, he lifts a light block the same distance, and it takes him the same amount of time. Which of the following is true? So if you remember, work done is equal to force times distance, and the force in this case is the weight of the blocks. So you have a heavy block, you have a light block. You're lifting them the same distance. So heavy block times say 1 meter versus a light block times 1 meter. Which one does more work? Well, the heavy block, right? Because it weighs more. So the work done is going to be more, right? Sorry, more for the heavy block. So this one's wrong. It's not more for the light block, and it's not the same for both blocks. So we have either A or B. Then we have the question of power. Remember, power is work divided by time. So I'll just go over here. Work is force times distance. Power is work over time, right? So we've got a heavy block and a light block. We already decided that the heavy block going the same distance as the light block is going to be more work. Now it says that he does both in the same amount of time. So more work for the heavy block in the same amount of time versus less work for the light block in that same amount of time, then obviously there's less power for the light block, all right? Because it is doing less work in the same amount of time. So that's going to be less power, all right? So bottom line, it's less. Less work for the light block, less power for the light block. Answer is A. All right. Now a worker is lifting boxes of identical weight. Identical weight from the ground onto a moving belt. When he first starts, it takes him 2 seconds to lift each box. Later in the day, when he's getting tired, it takes him 3 seconds. Which statement is correct? Right. So the first statement says, later in the day, less work is done in lifting each box. Later in the day, more work is done in lifting each box. What's work? Work is force times distance. Has the weight of the boxes changed? Has the height of the conveyor belt changed? The answer is no in both cases. That means the work is the same late in the day as it is earlier in the day. It's the same amount of work. So this has nothing to do with work. Okay, so let's check C and D. All right, so letter C. Later in the day, less power is developed in lifting each box, or more power is developed in lifting each box. Okay, remember, power is work over time. Work is the same in both cases, but later in the day it takes him longer. So if you have a bigger number in the denominator of a fraction, right? So let's just say that they're each one like 10 newtons, for example. So say 10 Newton box, all right, divided by 2 seconds versus a 10 Newton box divided by 3 seconds. Which one is a bigger number? It's that one. All right, so, and this is later in the day right there. So later in the day, it's going to be less power. All right, so that is letter C. All right, a little bit more about power. This table shows the times taken for 4 children to run up a set of stairs. Which child's power is the greatest? All right, so basically let's just look at what we've got here. We've got mass of the child, 40 kilograms. So that would be 400 newtons of weight, or 60 kilograms, 600 newtons of weight. So power is work over time, and work is force times distance. So we're not giving a distance here, but it's the same distance for everybody, right? Same set of stairs. So, and then you've got 2 options for your time, 10 seconds or 20 seconds. What is going to be greater power? Well, essentially you can eliminate both of the 20-second options because taking longer is less power, regardless of anything else. Alright, so that leaves a 600 Newton child or a 400 Newton child that are taking 10 seconds. 600 newtons, it's the same amount of time, right? But 600 newtons moving a certain distance is going to be more work than 400 newtons. So basically, there you go. Shortest time, biggest force. That's going to be your greatest power. Alrighty. 4 people of equal weight on a beach use different routes to get to the top of a seawall. Alright, so the top of the seawall, that's up here. Some of them are going to use the ladder, some of them are going to use the ramp, which they call a slipway for some reason. Okay, so essentially all of this is really kind of irrelevant. It doesn't really matter what path they take. What matters is their vertical distance that they get, right? So they're getting up onto the top of this wall. All of them weigh the same. All of them are ending up at the same height. So they're all doing the same amount of work. All right? All the same work. All same work. All right? So their work is all equal. That means the only question is who's faster? And that's really easy to find out, right? This guy, whatever this one is, that's the fastest. All right? So they are the fastest. They did the same amount of work in the least amount of time. So that's the correct answer. All right, and last one here. I want to do some actual work with numbers. If you have a calculator, grab it and follow along. All right, so we have a student who wants to find out how much power she uses when she lifts her body by climbing a flight of stairs. Her body mass is 60 kilograms, and you might remember that weight is equal to mass times g. Now we used g is equal to 10 meters per second squared, so we're going to have 60 times 10, 600 newtons is going to be her mass. All right, 600 newtons. So she takes 12 seconds to walk up the stairs. All right, the stairs are 3 meters high. Okay, so this is weight. All right, so I just clarified really quick. That's weight because we're going to be using work also. All right, so work, I'll do work in red here. Work is equal to force times distance. All right, this weight is the force. The distance is 3 meters, so we've got 600 times 3. All right, which is going to be 1,800 joules is the amount of work that is done. All right, so 600 newtons is her weight, and then that is the force, right? That's the force in the work equation. So weight is equal to force times distance. The force is 600. Height is 3 meters. Cool. Let's switch over to blue for the power there. All right, we'll switch to blue. So power is equal to work done divided by time taken. How long does she take? And the answer is 12 seconds to walk up the stairs. So the work done is 1,800 joules, and then the time taken is 12 seconds. So if we put that into the calculator, we will get 150, and the answer is watts. Watts is the unit of power. So 150 watts, 150 joules per second. And that's it. That's pretty much it. Pretty straightforward for the most part, I think, work and power. And there's some practice for you. So hopefully that'll help you get a handle on this.